All right, this is part two of the LS-Dyna joint series. Part two of 11. I'm gonna talk about doing a joint for a pinion and rack motion. Should be relatively simple. Most of these videos are gonna follow a very similar format. But what I like to do is to separate out each joint into a separate video, so I have a good repository of how to do the individual common joints, and we can take the information we learn here into a larger scale model just as easily as we do a simple model. Right, that's the idea behind it. Okay, so I'm gonna go over the basic concept, then I'm gonna go do a quick demo. Hopefully we'll keep it below 15 minutes. All right, so a pinion rack joint, just like the first joint I did around spur gears, right, requires 6 different points. This is the image from the documentation which explains what to do. But what I like to do is to lay it out because believe it or not, it took a little bit of time to actually decipher this code of exactly how this works. But as I figured it out, I definitely want to put it into a video and then presentation format, just so I have the information down. Okay, so there are 6 different points, right? 1, 3 defines the axis of the rotation for the pinion. 2, 4 is gonna along the center line of the rack defines the translation vector location. 2, 6 defines the axis which creates the plane for the rack, right? And that 2, 6 vector has to be parallel to the 1, 3 vector. The 1, 5 vector, which is point 1 and point 5, defines the radius of the gear, which then along with 1, 3 defines along with the point 1 defines the plane for the gear, and 1, 3 along with the 1, 3 defines the plane of the gear. That's a normal vector, and that's the plane, right? Okay, so going forward, what we need to do for something like this is that I still need to create 2 different rigid body. Now it could be my own created constraint order rigid body, like my CNRB, or it could be part of, say, a boundary condition like remote displacement, which also creates a CNRB, which I will demonstrate in the video. The 3 and 4 is actually what I'm going to be using. The palm parameter is the pitch radius. The pitch radius in this case essentially correlates the linear and the angular velocity of the pinion and rack. Okay, and then the relation basically look like this, right? So we have, this is the basic point illustrations, right? So point 1, 3 is the axis of rotation. Point 2, 4 is the axis of translation. Point 2, 6 and point 1, 3 are parallel to each other. This right here defines the plane of the rack. Point 1, 5 is the radius of the rack. I'm sorry, radius of the pinion. And this right here, point 1, 2, 3, 4, 5, 6, as you can illustrate on this screen, perfectly illustrates what needs to happen for the proper definition of a pinion rack joint. And then the reason we want the palm parameter to be the pitch radius is because if you look at the relationship between the angular displacement and the linear displacement, or angular velocity and linear velocity of the rack, right, they're essentially associated based on the radius of the circle, which is connecting with the linear portion of the rack. And the basic math here essentially is for each revolution, right? For each revolution of the rack of the pinion, the rack is going to travel by essentially the circumference of the circle, right? And if you look at the math behind it, what you essentially have is they're essentially correlated based on the radius of the circle, because we're essentially rotating by 2 pi every single time we rotate the gear. Right, and that's why the pitch radius is essentially what we're putting down in the palm parameter. Now, if the gear teeth do not match, you also have an additional relationship that you have to build, right? Like if you have a different sort of teeth size, the revolute size, the involute size. In this case, I kept it simple. Basically, you just have the same gear in this case. Okay, and then what the end result should look like is something that look like this, where you essentially have a pretty good mesh. There is no contact between any of the teeth, right? So this right here is purely based on the kinematic relationship between the pinion and the rack as I've defined in the joint. Okay, and that's what really a pinion rack joint does in essence, right? These 5 slides sort of very quickly summarizes sort of what happens in this type of problem, right? Now, what I'm gonna do next is I'm gonna do a very quick demonstration of something that look like this, right? The material for the pinion rack doesn't really matter. I'm gonna keep it as default. Just as anything else that I've done right? We're going to just quickly mesh this. It's really not about building a good mesh for these videos. So I just use a very small, very sort of like an arbitrary size just to have something going. Like you definitely want to make the mesh a little bit better. For example, you probably want to do like 0.5 in real life, but it's gonna take a lot longer to solve. So maybe make it a little bit denser just to look better. Okay, so once you have something like this, disable your body interaction because we're not gonna have any contact in here, right? And now what I wanted to do with these, right, is that I want to define the coordinate system just like with any other video, because I think it's a good strategy for how to handle this kind of problem, right? So if you remember if you look at the illustration here, these 6 points are essentially the origin of 6 different coordinate systems. I'm using them to find the location in space of how I'm going to find that point, right? Because coordinate system is a very convenient way to find locations, right? So right here, this XYZ coordinate is going to be the coordinate of my point 1, right? And then if you look at, say, for example, point 2, right? Point 2 can just be somewhere along that plane, for example. So one thing that we can do is, say, for example, let's just do, it doesn't really matter what it is in a lot of ways, because all we essentially have to do is to keep that point below it. So I'm going to change this to point 1. And then for point 2, what we should do here is, let's say, I'm just gonna go to point 2, and I'm just gonna global it. Now I already know what this is. So one thing you can do is to find this is say I'm just gonna select these 2 surfaces, and that's gonna put me at the center of my pinion rack right here. You see this right here, right? Now what you can also do is to make sure they line up. So that's another way in which you can do, but it doesn't really matter what that is, because point 2 just has to be inside the rack space, right, along the center plane of the rack. So given something like this, what we can do is, say for example, I'm just going to call this point 2, and just to be consistent with what I've done in my prepared material, I'm just going to do 5.756, and then I'm going to do 12.75, and then I'm going to do 14. So if you look at where this is basically just right around there, right? As long as it's inside the rack, it's good. Now, next one I want to do is point 3, which is essentially defining so from point 1, I want to define the vector that define the rotation axis, right? So all I have to do is duplicate point 1, and then I'm going to select this edge, and then bam. And you can see how between point 1 and point 3, I'm gonna call this point 3. Point 1 and point 3, I now have the axis of the rotation, right? Okay, now point 4, remember what point 4 is? Point 4 is basically just point 2, but translated along the axis of the rotation. And between point 2 and point 4, what I want to accomplish is to define essentially the vector of the translation, right? So in this case, instead of using 14, I just use 20. So if you look at between point 2 and point 4, all their xy coordinates are the same, but their z coordinate is different. Therefore, it's going to translate along the z-axis, right? And that's essentially what we want to accomplish with point 4. Now, point 5 is going to be essentially located at the center plane, same as point 1. So I'm just going to use point 1, duplicate it, call it point 5. And for something like this, right, what I like to do is to basically, because I'm in the center plane, so one thing we can do is, say for example, I can just select a point here. Like I could basically do, like say if I select this edge, right? Select the root of the gear, and then I'm just gonna do this. And then between point 1 and point 5, I will have the radius of the gear for the most part. Okay, but because we're not really defining a radius, what we're doing is to span that circle in space. So if you think about it, what we need is a axis here for the axis of rotation, then we need a plane for that rotation to occur, and that's really what the second point is all about. Now, in the example model that I made, what I actually did was I went to sort of global coordinate, and what I did was I did say 0.223, 4.2064, and 7.5004. Oops, I'm doing 6.223. and then I did 4.2064, and then I did 7.5004. And now what that will put is approximately the same location as I had before, right? And you see this right here, that point, and then with this point and this point. Oh, oops, I think I messed up. Sorry about that. Let me redo the point 1 here. Point 1 here is going to be right here. Okay, sorry about that. So between point 5 and point 1, I now have a radius of the circle, right? And that's really what you need to do for point 5 is help define the radius of the circle, define a circular plane for the rotation to occur. And then for point 6, which is the last one, what we want to do is to make sure point 26 is parallel to point 13, right? So point 13 is between this point and this point. Now point 26 obviously just has to be along the x-axis for them to be parallel, right? So all you have to do is to duplicate point 2, and then change the number to say from 5.756 to like 4. And what that will accomplish is that you will have 0.6, 0.26 is not going to be same as parallel as 0.13. You can sort of see that's the case, right? So you can see how the 0.13 and 0.26 are parallel to each other, and that's a requirement for you to fully define that plane on the bottom along the axis of the translations. Okay, and then with these 6 points, now once it's defined, it took a while to define these, and it has to follow very strictly to the requirement here in order for you to correctly define the kinematic relationship. But once you have that done, right, all you have to do is, so the way I do it is I will actually go into the text editor and actually edit the number directly into here, right? So I will basically take it to my other screen, I'll take it to the next screen, then I'll just copy the coordinate. Say for example, 1 is going to go in here, right? 6.223, 4.4316, 13.931. I just type them in here, right? So in this case, I already type all these numbers. So what I'm gonna do is I'm going to just copy this whole thing over, right? And then I'm just gonna insert a command snippet, and then we're just gonna bam, copy it in here. Now in this case, I know what I want to do is not using these two, so I'm actually gonna suppress it. I'm not even gonna create it because I know I'm not gonna need it. And then what I want to do here is to generate remote displacement. I could generate 2 different remote displacements. The first remote displacement is going to be on here, and it's going to essentially constrain everything except for the and I'm going to change this to actually to 0.1, and because that's the, and then I'm going to make sure that it's located in the center, right? So I'm going to constrain everything except for in the x-axis, right? So what I'm going to do here is just turn that to rigid, and this is going to convert that into a rigid body, and it's going to be assigned a number, part number 3. And then what I want to do here is I want to do a 360-degree rotations, and then I'm going to change the termination time here to 0.1 first, and then I'm going to type 360 down here, and that's going to rotate this thing by 360 degrees over 0.1 seconds. Okay, nothing special, right? Now the next one, what I want to do is to basically define a CNRB, constraint nodal rigid body, that's going to constrain the top surface of the rack like this, right? It's going to be located there. And in this case, I want to constrain everything except for the z-axis translations, right? The z-axis translation is the only thing I want to make sure I constrain. I want to leave it free, so that when the kinematic relationship is defined, I allow it to translate along the vector that I have defined from point 2 to point 4, right? And then with this, I create a second CNRB, and that's gonna be located right here, and that's gonna have only a z-axis translation degree of freedom free, and that's what 3 and 4 is for. 3 and 4 is referring to these 2 remote displacements. These 6 points defines a kinematic relationship, right? And then this right here, the 7.15, is in essence the pitch diameter. The pitch radius of the pinion. And that's essentially the parameter, that's the number that's going to correlate the angular and the linear relationship between the rack and the pinions. Okay. Now with these 4, I basically define everything I needed. I'm just going to call this the constrained joint, COR, rack, and pinion. And then just for consistency, as I always do, I will just create another quick database callout for mostly a join interface force and a D3 plot, and then that's just gonna write all the data, and that's really everything, right? So all I did to create a joint, right? You just have to basically, you know, put these into a folder and call this the pinion and rack joint. Now imagine if you are in a bigger model, you can just create a second folder for a different joint, another folder for a different joint. And those coordinate systems, we're not using them for anything other than to trace it into the how we trace the coordinates of these points. You can even suppress them at this point. It doesn't really matter. I'm not suppressing them because I'm actually using one of them for defining the rotation, right? Which is helpful. But most of the time, you're not going to use these points, right? Because we're not really using them as coordinate systems. You're all using them to find the location of the point, so we can properly define the kinematic relationship. And once it's done, you should be able to see a video that looks like just like this. And that is how we do a pinion rack joint. All right, hope this helps. Thank you very much.